Hi, everyone. My name is Zhihao. I'm currently an assistant professor at Carnegie Mellon University. So I was okay. It's fine. Yeah. So I was, I think back to like 10 years ago, I started my PhD at Stanford, and I was working on the Legion runtime system, and then switched to building applications on top of Legion. And today, most of our research focuses on building systems for machine learning using Legion and FlexFlow. So I mean, probably many of you have tried some of the large language models using GPT to generate as chatbots. And today, large language models has been widely deployed in many tasks. But on the system side, these models are actually very slow and expensive to serve. So if you want to serve a Llama 3 405 billion parameter model, which is an open source model, this is not the largest one. I mean, GPT-4 anecdotally is much larger. But for this Llama model, you need actually more than 40 GPUs to serve. It's not only expensive, but also very slow. So if you want to generate 256 tokens, which is the average length of a response, it takes around 40 seconds. That's why you have to wait a while for the model to generate a response. And also from a system perspective, we not only care about latency, we also care a lot about throughput. But for large language model generation, you need to have maintain KV cache for each individual request in order to avoid redundant computation. And that KV cache actually takes gigabytes of GPU memory. And as a result, we cannot serve a large number of requests in parallel. So our systems are built on top of Legion. And the central one is the FlexFlow distributed runtime. You can think of it as a domain-specific application that use Legion for doing scheduling, coordination, and we use NVIDIA and AMD libraries for doing all deep learning computation. And on top of FlexFlow, we now have three main directions. So the first one is on the training side. We call it FlexFlow compiler. So the idea is that because in order to parallelize model training across devices, it's actually non-trivial to figure out what's the best way to do parallelization. And the FlexFlow compiler will do automated end-to-end optimization that returns a fast parallelization strategy. And Colin's talk, so the talk after mine, will cover the training part. So this talk will focus on the serving part. And we build system to enable low latency and high throughput large language model serving. So some of you may wonder why we need a task-based solution for large language model. I mean, given that most of today's large language models are based on transformers, right? It's a static architecture. The computation is predictable. So why we need a task-based solution? And I would argue that large language model applications are actually becoming more dynamic and heterogeneous. So what do I mean by that? One concrete application, which I will cover later, is speculative decoding. So in order to improve the performance of large language model serving, so speculative decoding is a very common technique. And that actually involves you, in addition to host the target model, you also need multiple draft models. And you need to coordinate their execution in a dynamic way. So I will show how we use the Legion runtime to optimize for speculative decoding. And we're also seeing increasing intra-model heterogeneity. So within a model, most of the LLMs are moving from single modality to these multi-model serving scenarios, where you combine inputs from text, images, videos, and audios to generate a response. And different modalities actually involve different compute workloads and different characteristics. So that requires some non-SPMD solution. In addition, we're also seeing this intra-model heterogeneity, where instead of just serving a single model, we actually need to combine different large language model agents. And so in many cases, these requests are described by a control flow graph with multiple models, and you need to follow this data dependency to generate response. And this is also called compound AI systems recently. And we're also seeing increasing inference time compute. So instead of just generating a single response, we want to do some reasoning and search. I mean, we can apply search techniques or apply reinforcement learning to optimize and improve the generated result of the LLMs. And all this dynamism and heterogeneity are hard to be effectively supported in existing SPMD approach. And that's also why I think task-based solution, the Legion runtime system and Realm underlying task-based solution, are a very good fit for these types of application. And I will talk about some of them in this talk. Okay, so first, for the first half, I will talk about, on the serving side, how we build FlexFlow Serve to enable low latency and high throughput large language model serving. So to give you, given this is the first LM talk of the retreat, I want to spend one slide to give you a brief overview of how we serve large language models today. So the approach is called incremental decoding, or sometimes they call it autoregressive decoding. The idea is that the input to the model is just a prompt. It's just a sequence of tokens, and you go through, in each iteration, you go through all these transformer layers to generate output distribution. And based on this distribution, you can select the next token. And this token will be appended to the input. And now you can go to the next serving iteration. It will generate a response, it generates a new token, and we serve this in an autoregressive way until we reach out to the end of sentence. So there are some issues, two main issues with this autoregressive decoding approach. The first one is that it actually offers very limited degree of parallelism. Note that for all these iterations, we cannot run them in parallel on GPU because of the data dependencies. But by serving them sequentially, we cannot fully leverage GPU compute resources for serving. And based on our profiling, so large language model computation, serving computation is largely bottlenecked by memory access. So we actually achieve around 76% of the peak memory bandwidth, but only around 2% of the compute bandwidth. And so as a result, the model serving part cannot fully leverage the GPU power. And for FlexFlow Serve, the key idea is to try to avoid using this autoregressive approach where we use large language models as a parallel token tree verifier. I'll explain what I mean by this in the next couple slides. And this actually allows us to significantly outperform existing serving systems. And we also achieve much higher efficiency. And the key idea is to reduce GPU memory access. And of course, we guarantee the same level of correctness. So the results are guaranteed to be the same as using incremental decoding. So FlexFlow Serve is based on the idea of speculative decoding. So for those who are not familiar with this technique, so we can, the key insight is that we can use a small speculative model. We call them SSMs. We can use them in the autoregressive way to try to predict the large model's output. And so the small models runs much faster than compared to the LLM. And in addition, once the small model generates multiple outputs, we can simultaneously verify all these outputs. We can append all these outputs to the LLM and to use the LLM to generate an output token for each input. And when it comes to the verification, we try to verify whether the output of the large model is the same as the small model's prediction. Okay, so in this case, for the first token, they are the same. And we can also verify the second token. But for the third token, there is a mismatch because the large model's output disagrees with the small model's prediction. And in this case, we just stop our verification here. And this allows us to verify generates three tokens. And the key idea is that we only access the large model once, because all these three tokens are verified simultaneously. So this is a technique to reduce the memory access. And so how FlexFlow Serve leverage speculative decoding? So our idea is that instead of using a single small speculative model, we can collectively let multiple models to make predictions. So different small models may make different predictions. And we organize all these predictions in a tree structure. So in this tree, the path from root to every leaf node is a potential candidate. And we can send this tree structure to the LLM for doing, we call it tree-based parallel decoding. So the large model will generate one output token for each input. And this, so based on the output of the large model, we can construct a verified token tree. Yes?
I mean, so just intuitively, like how good do the SSMs have to be where they're actually getting a significant number of matches like with the real LLM? Like if they're not, like, if the SSMs are really bad, you would never actually get a match, and then so you would spend a lot, you would basically fall back to actually, evaluating the LLM one token at a time.
Yes. So we do this in an adaptive approach. So we try, the scheduler will first try to let the SSMs to do speculation. And if for the SSMs that are very bad, we will just discard them. And for those that are good, we can allocate more tokens. So there are some dynamism on the scheduler side. Okay, any other questions before I continue? Awesome. Okay, so based on the verified token tree, we can just follow the tree from the root node and follow the correct verification all the way to a leaf node. And this allows us to verify more tokens. And all of these verified tokens can be appended to the previous prompt for doing the next iteration of decoding. And so there are some challenges we have to address. First is how do we construct this token tree? Because you want the token tree to cover the correct answer so that you can decode more tokens. And how to verify token trees correctness quickly. So we propose, this is more on the ML side, we propose a boost tuning technique to maximize the speculation results, and we use a tree-based parallel verifier. So the high-level idea is that we can construct ensemble different small models from different sources. We can quantize large model, we can distill the original model, or fine-tune these some small models. And each model will give us some predictions organized as a token tree. And we also have techniques to collectively train multiple SSMs. So the idea is that for each SSM, because it's much smaller, it's hard to expect it is good at every task. So we actually let different SSM to specialize in different tasks to maximize the overall coverage. And this allows us to consistently improve. So the y-axis is the speed up. And using more SSMs, we can consistently observe a performance improvement. And for the individual predictions of the small model, we use a tree merge. Right? We can merge all these subtrees into a global token tree structure. And once we have a token tree, we can use the large language model to verify the correctness of different tokens in the token tree. Okay, so there are some interesting GPU design details. Since we have many NVIDIA folks, I want to briefly elaborate more on this and hopefully to trigger some discussion. So in large language model decoding, existing kernels are optimized for this, I would call it sequence-based decoding. So if you send it a sequence of tokens, they can generate one output token for each input token. And the idea is that we can apply a causal mask. The key insight is that we don't want the model to see future. So that's why this causal mask guarantees that for one token, it can only see previous tokens. And if we use sequence-based decoding, then we need to launch one GPU kernel per sequence. And each kernel involves a different KV cache, right? Because the KV cache of a token depends on all previous tokens. So for different sequences, they have different diverged previous tokens, and therefore different KV cache. So this approach involves some redundancy, because there are some common prefixes. Some tokens are shared by multiple sequences, and you need to compute them multiple times if you launch separate kernels. And also, you need to maintain because they have divergent KV cache, so you need to maintain different versions of the KV cache for each sequence. And so our idea is to extend attention to tree attention. Meaning we can apply attention to arbitrary tree topology. And the semantic is that we guarantee it will give us the same output as sequence attention for individual tokens. So if you run attention on different sequences of tokens, they will give you the same result as running attention on a token tree. And so the key insight is that we use a depth-first search to linearize the token tree. Right? We visit them so that token tree, that the linearization follows the topological constraints. And then for each token, let's assume token I, we can generate the corresponding causal mask to satisfy this tree structure. So in this case, token I depends on 8, 3, and 2. Right? They only depend on these 3 tokens. And we can set the causal mask in a way that token I's result only depends on the tokens in its ancestors. And this allows us to launch a single kernel for the entire tree structure. So once we have tree attention, it will give us one output token for each input token in the tree structure. And this allows us to generate a verified token tree where a green edge indicates that the small model and the large model agree on the output. And a red edge indicates disagreement. And we just follow these, all the verified path from root to the leaf node and to decode more tokens. And how we implement this idea in Legion. So on the CPU side, we have request manager that do all the scheduling. So it will coordinate based on the request, it will decide a budget for each small model. And we use data parallelism. We assign each small model to one GPU and to run them in parallel. So in this case, you actually need multi-program, multiple data because each GPU is serving a different small model. And all these small models will make their prediction. And all these predictions are sent back to the request manager as futures. Right? So we aggregate all these predictions in the request manager and perform token tree merge. So it will merge all the predictions in a token tree. And then we run the large model verification using tensor and pipeline model parallelism on GPUs. And they will make predictions that send back to CPU. So in order to minimize overhead, we first do a very aggressive task fusion. So the entire small model computation is merged into a single Legion task. And also we apply Legion tracing in order to, because we are going to repeat this same pattern over and over again. So we just trace the entire pattern to minimize the Legion overhead. And so as a result, this allows us to reduce the serving latency by 1.3 to 2.4 times. Okay, and I also want to briefly touch base on another project based on FlexFlow. We call it Flex LLM. This is for low latency and high efficiency inference and path co-serving. So before I introduce this co-serving idea, I want to share what is path. So path is called parameter efficient fine-tuning. This is based on the insights that for most large language models, they are pre-trained on general data sets. And if you want to specialize it for different domain-specific tasks, you need to do some fine-tuning. And that can substantially improve performance for various tasks. But if you directly fine-tune the entire model, that's very expensive. Let's use the Llama 3 for 5 billion model again. If you fine-tune the model from scratch, that requires more than 200 GPU. Yes?
Yeah, so for the
Wait, can you?
A little bit more on the configurations you mentioned using,
Okay.
like you mentioned using 40 A100, and also you mentioned some of the performance number. So how these GPUs are connected and what kind of setup are they?
Oh, that's a great question. Yeah, so I think we use 4 GPUs per node. That is this on the parameter supercomputer. We use 4 GPUs per node, and I think we tried different number of nodes. And we also tried, because for these 14 GPU numbers I gave, this is based on 40 gigabytes GPU. And we also tried on 80 gigabytes GPUs. We have the performance results in the paper. I can share with you offline. Okay, yeah. So if you directly fine-tune the model from scratch, that requires a huge amount of GPU resources. And as a result, it's more common today to do parameter-efficient fine-tuning. The idea is that we try to freeze the model weights and only inject some low-rank matrices. So in this case, instead of fine-tuning the weights matrix W, we try to fine-tune 2 low-rank matrices A and B. And we update the weights in a way by multiplying A and B. So in this approach, we only need to introduce a small number of parameters for each fine-tuning, model fine-tuning, and this also lowers the memory overhead. And so how we apply this fine-tuned model? Today, this shows a typical workflow. We start from a pre-trained large language model, and for different tasks, we apply different fine-tuning techniques. So we can apply LoRa, adapters, or IE3. And each of these adapters, once we have these adapters, we can serve these path-based models for different tasks. And one interesting thing is that we have seen before, the model serving is mainly limited by memory access because of this autoregressive nature. But on the other hand, if you look at the model fine-tuning, that is purely based, bottlenecked by compute resources. And the key difference is that for fine-tuning, you already know the ground truth, right? You know, you have the training data sets, and you know what are the tokens you want the model to generate. And this allows you to compute all tokens within a sequence, instead of just computing one token. So this key difference makes fine-tuning and inference completely complementary workloads. You know, one is bottlenecked by memory, the other one is bottlenecked by compute. So in this project, we want to improve the GPU utilization for both fine-tuning and inference. And our idea is try to co-serve these 2 systems. So both inference requests and path requests are sent as services, are provided as services by our system. And then we try to combine the memory-intensive inference workload with the compute-intensive fine-tuning workloads. And this allows us to use less GPU resources because these 2 workloads, they can share the same model weights. They can share the LLM model weights. We can also fuse the GPU kernels. And this results in higher GPU utilization, and we also preserve the inference service level objective. Yes?
So maybe just for intuition, I'm wondering how you actually get the overlap at the same time, because often as many of these, like the compute-bound kernels for the GPUs, right, they take kind of all the SM resources, but like the register file and the shared memory.
Yes.
So you'd actually have to have another kernel, running on the SM at the same time to get some.
That's a good question.
Overlap.
So yes, so for I think that's exactly what I have in the next slide. Right. Yes. So how we actually let them share resources. So this shows illustrates the idea of confusing, co-serving inference and path fine-tuning workload. So first, we try to schedule inference workloads, and because inference workloads, they are served in an online fashion. So based on the number of requests you have to serve, they may use different portion of GPUs. And we try to complement this with the path fine-tuning workload. So first, we interleave them with the forward of fine-tuning and backward of fine-tuning. Okay, so for the forward of fine-tuning, we can actually fuse the inference and fine-tuning workloads into the same kernel, right? Because both of them runs the forward computation of LLM. You can fuse them in the same kernel, and they are launched in the same legion task. And for the backward part, we cannot do kernel fusion because the backward part, they access the model in the opposite direction. So in this case, we parallelize the inference and the fine-tuning backward using different Legion tasks, and Legion will do the parallelization. Because these tasks do not have any dependencies. So Legion scheduler will schedule them using different CUDA streams. And our observation is that by introducing some pathed backward tasks, it will not prolong the execution of the inference workload. Okay, and so the key insight is that we schedule this dynamically because we don't know the inference workloads statically upfront. This is based on the online fashion. And that's why we dynamically decide how much fine-tuning workloads to inject to each serving iteration. Okay, so one challenge in this approach is the mismatch between inference and fine-tuning. So inference, as we have seen before, is based on this token-level decoding, where you generate one output token and you append it to the input, generates the next token. So for inference workload, it has a much lower latency and requires much smaller memory for saving activations. But on the other hand, for fine-tuning, where you send the ground truth to the model, and the model will compute gradients for all input tokens simultaneously. And as a result, it has a much longer per iteration latency. It takes longer to run for one iteration because there are much more tokens. And it also involves much more memory because the issue is that in order to do backpropagation, you need to save intermediate results. And that requires a substantial amount of memory. So in FlexLM, we introduced two techniques to reduce the per iteration latency and the memory requirement, so that to make these fine-tuning workloads compatible with inference workloads. So this allows us to serve them jointly. Okay, I think I will skip the details of these two techniques, but just to show that we leverage the model training details to reduce the granularity of fine-tuning. And we also have different memory optimizations to reduce the memory requirements. Okay, so how it actually works inside the Legion and FlexFlow stack. So for each pathed model, we send it to the FlexFlow compiler, which is the next talk. And the compiler will give us, tell us how to parallelize the model fine-tuning. And we send this decision to the request scheduler. That will dynamically decide how to combine inference and fine-tuning workloads. And so this configuration will send to the distributed co-serving runtime backed by FlexFlow and Legion. Okay, and so we try to compare our co-serving technique with existing approach that use separate systems. So if you don't do co-serving, one alternative, the current solution is to serve fine-tuning and inference on separate GPUs. You can have one cluster for serving, one cluster for fine-tuning. So in this case, we use 16 GPUs in our experiments. So when the inference request arrival rate is low, meaning that you don't have that much inference workloads, then you can just allocate a small number of GPUs for inference and most of the remaining GPUs for fine-tuning. Okay, so in this case, the separate systems approach achieves a similar throughput as ours for very light inference workloads. And as we have more inference requests, so in this case, you need to allocate more GPUs for inference and reduce the number of GPUs for fine-tuning. And in this case, we can achieve 1.6 times higher fine-tuning throughput for medium inference workloads. And the very interesting part is when you have relatively high inference workloads. So in this case, you actually need to allocate all the inference, need to allocate more than half of the GPUs for inference. And remember that fine-tuning needs more GPU. So in this case, you cannot achieve, if you use separate systems, you cannot do any fine-tuning workloads once your inference arrival rate is high. But yes, this is my last slide. Yes, and this allows us to. But on the other hand, we can still preserve more than 80% of the peak fine-tuning throughput. Okay, so there are also some things I think we can also discuss them offline. Something about the challenges of using Legion for doing low latency ML computation, and also want to acknowledge all the contributors of the FlexFlow ecosystem projects. Okay, with that, I would like to conclude, and I'm happy to take any more questions. Thank you.